Okay. Hi, everyone. Welcome to the first talk of our AIH Institute seminar series. We are very fortunate today to have this series kicked off by a talk by our friend Sanjay Shakkottai from UT Austin. He will be talking about resource allocation through learning in emerging wireless networks, 5G and beyond to 6G. So without further ado, Sanjay, you can start pretty much anytime you like. And for our audience, if you have any questions, please let us wait until the end of the talk, and then we will have an interactive session towards the end of this hour. Thank you very much. And Sanjay, again, welcome, and thanks for giving the talk today.
Wonderful. Thank you very much. So yeah, I'm going to be talking about resource allocation through machine learning. And since this for the in the context of the AI Edge Institute, I thought it would be a good idea to just start off talking about what the theme of our proposal is, just to get started, and then try to sort of place the talk within the context of where our proposal is. So again, the first part is basically from our proposal. Essentially, if you think about it, when we are going from 5G to 6G and beyond, there are several challenges in sort of emerging wireless networks. The first is increased heterogeneity, meaning the types of devices, the access patterns are going to be very, very different. There'll be many deployment scenarios. It's from urban to rural to time of day, and it's going to, as the cell sizes shrink and the spectrum characteristic and availability changes, this heterogeneity is going to increase quite a bit. The demand is also going to be high because several applications are very data and bandwidth hungry. And this essentially means that you cannot solve sort of heterogeneity problems and resource allocation problems simply by over provisioning. We need to sort of think about efficient allocations as well. Third interesting thing that's happening is that there's increased flux in the network. So given the heterogeneity and the scale, the frequencies which you expect to operate in, the footprints of cells will shrink. Edge users will connect to diverse devices and jump from one interface to another. So we are thinking about, what stationary regime means, we need to rethink about it. So normally you think of sort of resource allocation strategies designed for the steady state. In the wireless, the basic time scale you think about is a millisecond. So if you are thinking that systems remain roughly stationary on the order of minutes, you got tens to hundreds of thousands of slots, and so steady state, the way we have been thinking about it in wireless networks, makes sense. However, if you start scaling these sizes down, we need to think about algorithms that perform well even in the transient, as it were. So these are some things we need to keep in mind when we go from 5 as the generations of the wireless network scales up. And again, from our proposal, the vision is that we have a distributed the way we want to address these kinds of things is through a distributed intelligence at the network edge. What does it mean? It means that instead of having a single large controller, we want to have much simpler controllers interacting with each other. These controllers will learn and adapt, meaning to handle heterogeneity, they're going to adapt in a scenario-specific manner. So parameters will not be chosen globally and statically. They will be updated locally by learning. The platforms which to support these kinds of things need to happen. So they need to be open interfaces that will enable these agents to interact. And the goal is to manage heterogeneity, enable scenario-specific network optimization, and provide short-term guarantees. So this is sort of if we had to summarize the resource allocation side of the story in one slide from the AI's proposal, this is the way at least I think about it. Okay? So this is just as background to place in context what I actually want to talk about. So let me actually get to the talk itself. So I want to talk about two specific problems today. One is a network algorithm design problem, where I want to talk about scheduling to satisfy ultra low latency requirements. The second is a network operations problem, where we want to sort of tune parameters in the network to enable scenario specific deployment. So I'll talk about each one. And I'll try to end by around 12:50, I guess Eastern time 1:50, so that we have a reasonable amount of time to actually chat after the talk. So the first is joint scheduling of URLLC, or ultra reliable low latency traffic, and mobile broadband traffic, which is what we think of as regular traffic. This joint work with Arjun Anand, who is at Intel Labs, and my colleague Gustavo de Veciana. So if you think about, so let's think about the 5G scheduling. What are the types of traffic we are going to see in 5G and beyond as well? Okay. So one category of traffic is the mobile broadband traffic, meaning you want to have high data rates, reasonable delays, order of tens of milliseconds. Think of file download, video streaming, web browsing. The usual applications is what I would think of as EMBB. The second category of traffic is called URLLC, or ultra reliable low latency communications. In this case, this is for mission critical type data. We are talking about sub milliseconds, like 1/5 of a millisecond type delay. And you want to have very high reliability. There again, so mission critical control messages. So low bandwidth, but very high reliable, very low delay is what we are talking about there. And the third is called MMTC traffic, essentially massive machine type communications. This is like IoT type devices. Delay is not the constraint, neither is throughput. It's essentially you want to have simple protocols, very long battery lives. So I'm not going to talk about MMTC today. I'm going to talk about the focus of the talk today is between EMBB and URLLC. That's what I'm going to be talking about in the downlink setting. And the goal of this first talk is to look at how simple online learning type approaches can handle a combination of these types of traffic. So just so that everybody is on the same page in terms of the wireless system, let's talk about how resource allocation roughly happens. So resource allocation, when you have these two types of traffic, happens at two time scales. First is the slow, quote unquote, slower time scale of EMBB traffic. So EMBB meaning high data rates with several milliseconds time scale. So what you have is time. If you look at in the figure, the x-axis is time, y-axis is frequency. In time frequency, a time slot is order of 1 milliseconds to several milliseconds. So that slot is a millisecond time scale, and you want to allocate this slot. You want to share this among different users who are downloading, say, video or high bandwidth traffic. The usual story in wireless scheduling applies here. The channel is time varying. It's different for different users. So you want to use some opportunism ideas to pack these users in an efficient manner. Okay. This is now a 20-plus-year-old story. The second type of traffic that comes into this is the ultra reliable low latency communications. So these have really tight delay constraints, sub millisecond. If you look at the EMBB traffic, the scheduling happens at these slot boundaries. If you decide that you're going to also deal with these low latency traffic on the same time scale, so let's say some traffic arrives at these points, then you need to wait for all of it till the next slot boundary so that you can schedule that in the next slot. This is not feasible because you're already on a millisecond delay, whereas what we are looking for is sub-millisecond delays. Okay. So what is proposed is in these kinds of systems, overlay this slot with mini slots. So you see much smaller slots here overlaid. And these mini slots are 1/8 of a millisecond. So when URLLC traffic arrives, you don't queue it. You just essentially just push it into the next available mini slot. So there are no dedicated resources for URLLC traffic. You just need to multiplex these two types of traffic dynamically. And what I mean by multiplex is just, if you have some URLLC traffic, there's already a pre-scheduled EMBB traffic, which is transmitting here. Well, you just overlay it by some other traffic. So either by puncturing or just superposition, meaning you're going to hurt the EMBB traffic, but this traffic is presumably coded strong enough so that it's actually received by the internet receiver with high reliability. and with extremely low delay because you're working in a much smaller time slots. So hopefully the model is clear. Essentially, you've got slots which are carefully optimized with the usual utility maximizing wireless schedulers. And you've got mini slots where you do essentially preemptive scheduling as soon as the traffic arrives with no queuing, which is going to damage the existing transmissions, but you'll deal with the damage as post fact. Okay. So the goal is essentially now to figure out how to overlay this traffic in an efficient manner, meaning you want to minimize the damage to existing traffic and still get these things through successfully. That's the problem here. This is the URLLC and EMBB co-scheduling problem. And what I'm going to talk about is essentially a stochastic approximation approach to think about this problem. As I mentioned during the last few minutes, EMBB traffic, it suffers throughput loss when punctured. Okay? The reason is that when some overlay occurs on the EMBB traffic, essentially there is a loss of the data of the EMBB traffic, and this needs to be decoded with this part being punctured, erased, or some version of noise, loss of this kind of this part of the data. If you look at where the flexibility is, so let's say that this was a particular time slot where this packing happens, and I'm just zooming in on a particular section. So some URLC traffic arrives at this point, needs to be scheduled on. So you have the flexibility to either put it down here and halt EMBB5, put it up here, halt EMBB4, or put part of it here, part of it here. So this axis is frequency. Okay, so you can place it along the y-axis in different places and differentially hurt different users. And the goal is to sort of maximize some total benefit to the system. In addition to sort of the utilities of these various users, the channels have different EMBB dependent user rates. Meaning, look at this frequency band. If I decide to schedule user 4, you're going to get across in this entire band, you may be able to get a high rate because the user 4 is in a good location. On the other hand, if you schedule user 5 in this whole region, you may get a much lower rate because user 5 might be in a poor location. This is again nothing new here. This is like a 20-30-year-old story now, that channels are user dependent, and when you schedule when you're scheduling, you want to be opportunistic, depending on the user's location and user's requirements. So again, I'm not saying anything new here for people who played with wireless. I'm just setting the stage of the usual wireless problem here. The only quirk is now I have a chance to puncture the URLC traffic. I need to puncture it. The question is, where do I puncture it? Hopefully the problem is clear. If you want me to stop or have any questions, by the way, just jump in anytime you want. So before we start talking about our algorithm or what we want to do, I want to just go through a very simple, a toy thought experiment of where would we puncture. Let's forget utilities. So every user has this, users are all have similar utilities. Let's say that the channels are, in this simplest model, the channels can be one of two different rates, rate 1 or rate 2, and it's time varying. So what I've shown in this cartoon is essentially the following. This axis is time. This axis is frequency. Okay. There are two users, EMBB1 and EMBB user 2. There's no puncturing yet. This is just the old opportunism story. Okay. Or in fact, the old non-opportunism story, in fact. So let's say that the channels can be for each user can be in one of two different states and they're independent, meaning the channel is equally likely to satisfy rate 1 or rate 2. Okay. And because there are two users, therefore, the rates you can get over time is user 1 can support 1, user 2 can support 2. Both can be in 1, both can be in 2, or user 1 in 2 and user 1 in 1. Okay. These are the four possibilities. And on an average, each one of them occurs 1/4 of the time. If I wanted to just do the usual static scheduling, I'm just going to slice up the channel half and half and say that this is for user 1, this side is for user 2. Then you can see that the average rate you can get to user 1 is 3/2, because half the time it gets you rate 1, half the time it gets rate 2. And similarly for user 2. This is just the old round robin, now 50 years old or even more. Now let's puncture on top of it. Okay. Suppose I randomly puncture. So I don't care about who's transmitting where. I just puncture. So when URLC traffic comes in at any point in time, let's say that I will just let's say the traffic intensity is such that it requires half the bandwidth. Then I will puncture 50% of this and 50% of this. Okay. This is just equal under at least an expectation. This is random puncturing. So if you do random puncturing, you see that you have lost half the rate for each one of these users because it's just random. And therefore, the long-term rate for each EMBB user is going to be 3/4. Are you with me so far? Okay. Now, let's do opportunistic puncturing. So suppose I say that I want to puncture intelligently in this system. If I look at this time slot and I have to puncture 50% of it, then I don't want to puncture half of user 2 and half of user 1. I'll spend all my puncturing only on this side because I know the rate is low anyway. So in terms of the overall hurt to the system, it's better to puncture user 1 completely and give it nothing, and user 2 is unaffected. In this case, so what would I do? Then I would, opportunistic puncturing says that I would puncture whenever I can, whenever possible, I'll puncture all of 1. And when I don't have any options, meaning in this case, for example, both are 1, I'll puncture half of this user, and both are 2, I'll again puncture half of this user and half of this user. Opportunistic puncturing is clearly better than random puncturing. It's obvious, and just if you think about it, what I've said, nothing is really deep here. I'm just showing you that if I'm careful in where I puncture my EMBB traffic, then I can do much better. I can, instead of getting a 3/4 rate per user, I can improve much more to 7/8 rates per user. So
Sanjay, can I interrupt?
Yeah, please.
Yeah. So in the second block and the second and third column, you could potentially just do the same thing you did earlier, right? Which is you could just puncture all of 1 and all of 2 on the top, right? You don't need to do it the way you're doing it right now. Or am I missing something? I apologize. I joined a little late.
No worries. Let me make sure I understand your question. So this is not, in this figure, there's non-opportunistic puncturing. So I puncture half of this, puncture half of
I understand.
Okay.
Right. Now let's look at the opportunistic. Yes. Yeah.
Okay. Yeah. So here I will puncture user 1 only. I need to puncture half the bandwidth.
That's clear.
That's clear. In the second one, both the users are in bad state.
Yeah. But you could puncture only the top one still, right? You could do any.
But why should I? I mean, I'll be fair. I want to give equal rate to both.
I see.
There is no benefit, at least in terms of some throughput, of puncturing the top one.
I see. So, right.
But
there is no loss.
Doesn't matter.
But
any puncturing is fine.
Yeah. That's all I was trying to say. At least from a throughput point of view, it doesn't make any difference, right?
Throughput point of view. So all I'm trying to do is to give equal rate. That's why I punctured half and half. Okay. But from a throughput point of view, I could puncture wherever I want. In these two cases, it doesn't matter where I puncture. The throughput is going to be the same.
Right.
Okay.
Good.
And so this is a very old story. We all know that if you are opportunistic, there's benefits to be had, and there's a puncturing side of the story as opposed to scheduling side of the story. But it's nothing new. Essentially, it's the same principle. Okay. So now let's change the story and let's actually talk about opportunistic scheduling instead of non-opportunistic scheduling itself. So instead of doing the basic scheduling where I do just statically give half the bandwidth to user 1 and user 2, I'm going to be opportunistic and say that in the first time, since user 2 had the better channel, I'll give the entire bandwidth to user 2. Okay. This is just opportunistic scheduling. In the second one, in the second time slot, I'll share again between user 1 and user 2 because there's no gain, there's no benefit in opportunism here. Same in the third time slot, I'll give it to both. And the fourth time slot, I'll give the entire thing to user 1. So the splitting is no longer this central line, but this. This is the opportunistic scheduler. That's all I'm saying. And because you do opportunistic scheduling, you're going to get an improved average rate. In the 1.5 rate per user, you can see that on you're going to improve here, and you'll get to 7.04. But what is interesting, at least in this example, is the following. Now, if you do puncturing on top of this, okay, then if I ran, you can see that there is no benefits you can see in any of these slots to be intelligent in puncturing, because here, wherever I'm puncturing, I'm hurting user 2, and in the equal way. Here, at least from a throughput point of view, just to continue the point you made, wherever I puncture, in terms of throughput, nothing changes. The same in each one. So there is no gain with opportunistic puncturing when I'm doing intelligent scheduling in the first place. Okay. This is just a small observation right now that somehow puncturing problem becomes much easier if you're doing, if at least in this 2-state symmetric everything, the scheduling in the first place was done in an intelligent manner. Is it clear so far what I'm saying? Okay, let me just continue. If you have any questions, stop me. So the question is, how does this generalize? And also, I made this story about stochastic approximations and learning and all that. Where does any of that come in here? This is just to set the stage. So now let me talk about the problem itself. So I'm going to just, given that this crowd has good background of wireless, I thought I'd just talk about the utility maximization problem in this setting. The utility maximization problem here, you can formulate an offline problem, and we know how to do this kind of thing for more than 20 years. So let's talk about this problem, just so that everybody has a notation straight. That's really why I put this slide here. Okay. So what do you want to do? So little u is a user index. Each user has some utility function. You want to maximize the total utility. So maximize the total sum utility across all users. And the utility should be function of the rate that each user gets. This is the rate to the user. Okay. And what is the rate? The rate is the following. The way you want to think about it, so-called static split rules, again, going back to early 2000s, or even late 90s, is the following. For each user and for each channel state, you decide a fraction. You say that phi, this is the fraction of traffic of the bandwidth that you're going to give to user U in channel state S. And phi encodes over all possible channel states and over all possible users. Similarly, you decide, if you knew the statistics of how puncturing traffic is going to appear, you'd say that when in for user U in channel state S, this is the fraction of traffic you're going to puncture. Okay. And gamma encodes now all what fraction in every condition did you puncture. Then your rate is some function of how much bandwidth you allocated and how much you are punctured. To dig a little deeper into that, it is the following. Well, the rate to any particular user should be the following. First, in each channel state, there's some spectral efficiency. So that's the baseline. You're not going to get the entire bandwidth. You'll get some fraction of it. So you have to thin this down. Because of the puncturing, now you need to see how does puncturing actually affect the traffic. There is some function that affects it. And because of that, there's some loss rate that depends on the function which affects the puncturing, as well as the fraction that's punctured. All so far so good. And you need to average this over the demands. Here I'm assuming, at least for this offline formulation, we know all the statistics. So then I can figure out what's the rate that what's the rate that you're going to get, at least on an average, and then go and stick that back into the utility maximization problem, subject to the usual stability constraints. And you can write a joint EMAB scheduling and URL replacement problem. Okay. This assumes knowledge of all the statistics. The only twist to the usual story here is that there's a puncturing as well, and there's an extra averaging over the puncturing. Okay. Other than that, it's exactly the same story which we have thought of, which we have seen many times in the past. Okay. So
Sanjay, may I interrupt?
Please.
Why do you need to know statistical information here?
We hope we don't. I'm just sort of saying, I'm doing the thought I'm trying to do the analogy of, hey, if I was doing downlink scheduling, where I didn't care about queues, I would figure a static split rule, meaning what fraction of bandwidth in each state, and then come up with a time sharing rule. This is just the optimization problem. I'm not saying that.
Okay, yeah. All right, okay. So yeah, all I'm saying is that instantaneous would be fine, right? You don't
It
need,
may be fine, it may not be fine. We'll look at it. But the difference here is this puncturing is some weird thing that's going on here.
Sure.
That's there are two things which are going to be opportunistic. There is the scheduler, which the fraction of bandwidth to each broadband traffic needs to be opportunistic, and the puncturing also potentially could be opportunistic. There are these two different opportunisms and happening at different time scales, meaning at the beginning of each slot, you schedule users without knowing where the URLC traffic is going to come. That's the key. You don't know when traffic is going to come in the future. You need to make allocations. And if there's a lot of puncturing, maybe your allocation at the beginning of the slot might have been different if you knew that there's going to be a lot of tough stuff punctured versus very little punctured in the next slot. That's where sort of the some interesting things start happening here.
I see.
Okay. So what we can show here is the following, I think, interesting result, which is if you are just trying to do this with no puncturing, okay, if I was trying to solve this particular problem with no puncturing, then we can go back to Stoliar's gradient-based scheduler, right? Or which is basically the following. This goes back to 2002. Utility maximizing schedulers. What do? You look at the derivative of the utility times the rate. This is the max weight rule. So in the utility context, so it goes. There's like a 30-40 year history of these kinds of algorithms now. Okay, and what would you do? This goes back to what Ness was saying. You just do an online scheduler, which is look at the utility of whatever rate you're going to get times the spectral efficiency in that state. But what we have here is not just the utility maximization, but also a puncturing that's going on. So this is the claim that suppose you just randomly puncture in a non-opportunistic manner. You don't care what, whenever traffic comes, look at the vertical axis and just puncture wherever you want, just uniformly randomly across the time. And because of that puncturing, this is going to induce a particular rate that you're going to see in the past, right? The utility maximum in any particular time slot, the scheduler allocates decisions without knowing when puncturing or where puncturing is going to happen. Then at the end of the time slot, you look back and say that the rate you got was something else than what you thought you would get because you randomly punctured. Okay, it's not, I'm not trying to do any optimal puncturing here. The claim is that if the loss in throughput due to puncturing is linear in bandwidth, then this above algorithm is optimal, meaning there is no benefit to do opportunistic puncturing. You can just be random. As long as you do intelligent scheduling in the first place, then everything else can be random and then you'll get no additional gain. So this is not immediately obvious, and I think there's a nice insight in this problem. So it allows us to essentially schedule URLC traffic as and when it comes in just a random manner and still be provably optimal. I'll stop here for a second to make sure this point is clear. So among everything I've talked about so far, except for this point, the rest should be sort of, for people who have played in this space, should be obvious to anybody in this space. This is the first statement here, which is not clear why this has happened. Okay, so let me move. Let me give you some intuition on why this happens. Essentially, if you do opportunistic EMBB scheduling, it operates on the Pareto frontier, the capacity region. So there is no residual opportunism that is there in the system that's left. And so it turns out just being random and puncturing cannot get you any extra opportunistic gain in the system because you're already on the boundary, and essentially that's why random is good enough. However, if you use any other scheduler which is non-opportunistic, such that the system is not pushed to the boundary, then opportunistic puncturing can extract additional throughput for UMBP traffic. And so if you're using a suboptimal scheduler, you need to be, the problem becomes much harder for puncturing. Whereas we use the optimal schedule in the first place, in terms of throughput, then the puncturing problem becomes very easy. And so this is actually useful system design insight here.
So Sanjay, I am actually a little confused by this result. So when you're doing opportunistic EMBB scheduling, you may still need to schedule multiple users at the same time, right?
That's correct.
So in that case, won't non-random puncturing still help?
No, that's what we prove. If in expectation, the theorem is that, which is why this is not immediately obvious what I'm saying. I gave you some intuition for this. If you have linear loss, it turns out that in terms of long-term throughput, you get exactly the same utility as a long offline algorithm if you do the right opportunistic decision every time slot. With the rate being not the rate that you actually are going to predict you're going to get, but the rate which is based on a running average in the past. So it's the punctured EMBB rate is what we need to deal with. So the average effect of puncturing is somehow coming in the scheduler in what rate you're actually using to make decisions.
So could we say that after opportunistic scheduling, each resource is contributing the same amount towards utility maximization? So now whichever resource you cut out doesn't matter. User doesn't matter. Each resource contributes the same.
Exactly. You're using essentially that's exactly what's happening. And that's the generalization of this picture I drew in the beginning. In this case, the rate was the same. So there was nothing happening. As Bilal just said, right now, in a sense, if you do this, then the marginal utility is exactly the same. So it doesn't matter. So the puncturing can be completely dumb and still you're going to be optimal.
Yeah, I understand that. But I guess I was wondering why, when you're doing opportunistic scheduling, you're getting that type of a result where the resources are exactly the same. I mean, yeah, I understand if that's the case. Yeah.
Yeah. Maybe I can chat off.
Sure. I mean, I guess
the
that's
marginal utility is the same.
So
essentially, the marginal utility, exactly as Bilal said, happens to become the same when you do this.
Okay. All right. Okay.
And okay, I have only 15 minutes left. All right. So the story extends if you have other types of loss. So what I sort of shoved under the carpet here is how does puncturing affect throughput for EMBB? Okay. So what I talked about is something called the linear model. If I puncture 50% of the traffic, I lose 50% of the rate for EMBB. But maybe there are other types of models. Maybe there's a threshold model because it's strongly enough coded that up to some point it doesn't damage it at all, and afterwards it's catastrophic. Or maybe there's a convex model. So with some of these kinds of models as well, you can do a little bit more. You can run an essay type of algorithm, a stochastic approximation based online learning algorithm, and still get essentially asymptotic optimality results. Since I'm way behind on time, I'm going to skip on this and I'll come back to this if you're interested at the end of this talk. The main takeaway is simple adaptation, online adaptation can allow us to come up with scheduling for URLC traffic with very, very little changes to the system needed if you're using a good scheduler to start with. So I want to switch tracks. So these are the scheduling problem. For the next 15 minutes or so, I want to talk about before scheduling. So how do you tune the system for scheduling and where learning can play a role in this? This joint work with Iswar Tariq at UT, Rajat, who's at Google Research, Tom, Salam, and Milap, who are at AT&T Labs, and Gustavo, my colleague at UT. So in the first part of the talk, I talked about scheduling and basically said, yeah, there's channel rates, there's a channel state, which will lead to some particular rate, queue lengths, or whatever utility you want. Combine these two to make scheduling decisions. But when normal, and this is the way, at least you have thought about the scheduling problem. But there's an underlying problem here, which is where do you get the mapping from the channel quality to the channel rates? Okay, so we say, oh, okay, there's a capacity region and you can work on any point in the boundary of this capacity region. But in practice, we don't know what rates are sustainable for each channel state. So I'll give an example of what I mean by this problem. Okay, so let's say there are two users. There's one base station. There are two users. Okay, and this cartoon here is some representation of all possible channel quality indices you could have gotten for user 1, user 2 pair. This red dot means that user 1's channel quality is this, user 2's channel quality is this. This blue dot is a different such point. Each such point theoretically maps to a particular capacity region. What does it mean? If you look at the rates that user 1 and user 2 can simultaneously sustain, if you schedule user 1 alone, its channel rate is not great, so you're going to get this rate. User 2 alone, you may get a better rate. And when you co-schedule user 1 and user 2, if you're using MIMO or something like that, you could do potentially better than time sharing. So the point of this slide is saying that given any point in the capacity region, there is a rate region associated with this. For a different point, there's a different rate region. Okay, and when we make scheduling decisions, what we assume is that we have a mapping from channel state to set of possible rates. This table is somewhere there. And indeed, there is such a table. This is a CQI. This is a CQI to MCS table that's hard-coded into the base station based on lots of experiments. And you have access to this table. You have a user selection, and then use this table to figure out what rates are possible and schedule according to that. But let's now dig a little bit into how this table itself is created. Typically, it's handcrafted map. You do a lot of experiments in different scenarios and find a good mapping of from channel quality to the modulation coding scheme and use such a static map. However, we know that this map could potentially vary across environments. If you have a dense urban environment versus maybe a rural environment, maybe the kinds of the maps itself may be different. So the question is, can we go into the base station and instead of using a scheduler based on a static map, we'll not change the scheduler. We'll just try to learn the map itself online and see what we can get out of this. Hopefully this problem is clear. This is not the usual scheduling problem. This is actually the problem of learning a map from channel quality to set of sustainable rates. And then using that to make scheduling decisions and seeing what kind of improvements we can get. So the innovation here will not be in the scheduler at all. We'll just try to use the default schedulers. So if you want to learn such a map, let's just do something really dumb. This is not what we should do, but let's just start with this, which is there in a cellular downlink system, there are 16 discrete values for the channel quality index. The modulation coding scheme has 28 discrete values. What you need to learn is essentially, if you've got an end user system, you've got these many parameters, 16 times 28 to the n. And for each channel quality, for each vector of channel quality, you need to find the MCS that you want to choose. And if you just do a brute force computation, exhaustive search says that even for a 4-user system, if you search one, if you can get answer to just one query every millisecond, it's still going to take you an infinite amount of time essentially to figure anything out. It's 1.25 years for a 4-user system. So what am I illustrating through this? It's the following. So this is a particular CQI MCS. If I don't use any domain knowledge and I'm just going to completely be data driven, which is a bad idea, but suppose I just do that. What would the dumb thing to do here is pick a particular rate, user 1, user 2, schedule it. Maybe both transmissions fail, maybe, and in which case you basically say it doesn't work. Maybe it succeeds on the other hand. So it say it works. Then try some other rate point. Okay, this one may succeed or fail, and so on. Eventually, what you can do is to map out over the space what parts succeed and what parts fail for this one channel state. And then the boundary of this is the capacity region. Okay. Again, I'm being very, very pedantic and silly here. You can do something much smarter. But this is just to set the stage. Similarly, when I get a new different channel state, let's see what's going on. So sorry, when I get a different channel state, I'll get a different rate region. and so on. I do this exhaustive search, and I can potentially find the capacity regions for every possible channel state. However, there's a much better dimensionality reduction in this problem, meaning the following. We know that if channel states of two users are pretty close to each other, two vectors of channel states are close to each other, the capacity regions must essentially be the same. Okay, so that's the first point of dimensionality reduction, which means you don't need to learn for each separate point a capacity region. You want to first cluster the channel states in some manner. Okay, we don't know how the clusters look, and then for each region you want to find a capacity. You want to find the trade-off. That's the first point. Hopefully it's clear so far what I'm trying to do. I'm simply trying to learn the mapping from channel state to capacity to the rates, sustainable rates. And I want to do this in an efficient manner by using some clustering ideas. Meaning I want to cluster in the CQI space, saying all these CQIs are essentially the same. And the second thing I want to use is monotonicity, which we know from physics essentially. Meaning if a low rate is sustainable, then every lower rate is also sustainable. If a particular high rate is not sustainable, then every other high rate is not sustainable. So you have this natural monotonicity along rates. You want to use these two ideas and learn these. You should be able to get much better scaling in terms of how you want to learn these maps. Okay. So the system model is essentially the following. I have a system where I don't have a CQI to MCS table. So I don't know how to schedule, not because I don't have a good scheduling algorithm, but because I don't know how to translate my channel quality to possible rates that I could actually use to transmit traffic. So what I can do is to observe the channel state, try by trial and error, try a particular channel, try a particular rate, and get noisy ACNACs notification from the users. And therefore, I'm incrementally trying to build both this map and these maps. And I want to use these maps to actually build the CQI MCS table. And I want to do this as efficiently as possible, meaning I want to minimize something called regret, how much off I am with respect to a genie, which actually knows these maps. So what we have is an epoch greedy algorithm. I have 5 minutes, so maybe I will actually skip the algorithm detail because I have I want to leave at least 10 minutes in the end for actually talking about it. Essentially, it's an epoch greedy algorithm. For people who played with bandits, it's an online learning algorithm, which actually tries to cluster capacity region in an online manner, learn rates associated with it. So I don't have time to go through that. I'm going to skip the algorithm. And just get to the summary of this algorithm. It essentially tries to roughly partition the channel state space into clusters, improves these clusters, and while improving the clusters, makes scheduling decisions to learn the capacity region itself, and then use this learned clusters and learned capacity regions to actually make transmission decisions, and in a closed loop improve both the scheduling decisions as well as the clusters and the rate regions. That's a high-level summary of this part of it. But what I want to, and we can prove some regret guarantees for it, but that's not what I want to highlight about it. What I want to highlight is that these kinds of things are actually the bigger story here is online learning can be extremely useful even in such parameter tuning problems. So what we did with our collaborators at AT&T is the following: that so they have a very fine-grained 5G NR simulation, which basically has implemented the entire stack. They only and the protocols in great detail. The simulation there is on the channel model, and and they have pretty high fidelity models for the channel. But this indeed this is a simulation, and this system supports a multi-user MIMO as well. So this figure here describes quote unquote their system. So there's a traffic macro scheduler, there's a resource manager. The macro scheduler selects a collection of users, and then the resource manager gets access to the channel quality, and a particular table which maps channel quality to the MCS levels, and use this table along with users and the channel quality to make scheduling decisions. And there's a closed loop system that operates in practice. What we did is said that, okay, let us use our learning algorithm to learn this table, this channel quality to MCS table, using exactly the method we talked about previously. Okay, and then so we just plug this system into this, plug a learning algorithm for parameter tuning, and see is there any benefit that you can get in different systems. The first question, before even we sort of look at the performance, is the following. So we posited earlier that there is some sort of clustering in the channel state space, in the channel quality, meaning we posited that nearby channel qualities will have very similar capacity regions. Makes complete sense intuitively, but we wanted to see whether indeed the data supports that. And indeed it does. For the simulations we ran, we basically saw that all these blue dots are different SINR pairs. All the red dots are some other SINR pairs. The blue dots here corresponds to the blue capacity regions here. The red dots here correspond to the red capacity region there. So indeed that there is some low dimensional structure in nature which we can exploit. This clustering does, these simulations say that this kind of clustering does exist. Okay. Once you say that, okay, we want to do this kind of clustering algorithm, we can ask, can learning these kinds of maps actually improve performance in terms of two quantities? I care about probability of success for multi-user MIMO transmissions, and I look at average throughput for MU transmissions. Okay. So let's look at a small scenario first. There are only 4 users in this cell. What we use is 3 hand-tuned policies and 1 learning-based policy. If you look at these figures, for the first 10 seconds, about order of up to first 10 seconds or so, the learning-based scheduler is much worse than any of the hand-tuned schedulers in terms of performance. This is the throughput. The y-axis is the throughput, x-axis is time. Okay, you can see that even though it's initially bad, it quickly catches up and it meets the performance or slightly outperforms the performance of one of these 3 hand-tuned schedulers. So far good in this plot. It says after about 10 seconds, I'm not essentially losing very much compared to any of the hand-tuned schedulers. In scenario 2, so this is another channel scenario, and here again for the order of up to about 10 seconds, the performance of the hand-tuned schedule of the learning-based scheduler is learning-based map is poor, but over time it has outperformed all 3 of these hand-tuned schedulers. The takeaway from just this plot shouldn't be that, oh, learning-based schedulers are better than hand-tuned schedulers. That's not the message I want to convey here. Because indeed, if you look at this, the parameters that are converged to, I could have found another hand-tuned scheduler which could have met this one's performance as well. The point is that what this allows is scenario-specific optimization. That's really the message I want to push. That what you'd like really is a different table in different scenarios. What is being done today in practice is to have the same table in all scenarios, because there is no easy way to actually go and say, I'm going to figure out what is the right table for each scenario, which is why I think learning-based algorithms actually can have impact in the field. Now, if you make sure that you have a default table and then use a learning-based scenario to create a table and let that take over, you can see that you can essentially match what is the best hand-tuned thing you could have done in that setting, instead of using sort of a static one across the whole of across all base stations. Sometimes you get tremendous gains. In this case, you can see that after about 5 to 6 seconds, none of the hand-tuned ones were working well in this scenario, but the learning-based one does better. Again, I could have created yet another hand-tuned one, which could be up here all the time from the get-go. Okay, but because we had to pick one for all scenarios, you lose the flexibility to find the good map for each setting. this kind of story holds when I increase the scale of the setting from sort of 4 users to 7 users. And again, in a multi-cell scenario, you can do these kinds of things. Okay. I have a bunch of plots, but since I'm like 5 minutes over time, I want to get to the takeaway. The takeaway is not that learning-based approaches can give better throughput or better performance than hand-tuned and static maps. It's that it adapts better in different scenarios, and therefore it allows scenario-specific optimization. And going back to the beginning of the talk, I think that's one of the themes that our AI Institute really cares about, that you want simple AI agents that, because of heterogeneity and so much diversity in the system, you don't want to use fixed parameters. And so we should start thinking about these kinds of algorithms. Because it's just a small little thing. What we are thinking about in the setting of our grant is a much bigger story, but these are the kinds of building blocks we should start thinking about. I'll stop at this point. I'm happy to just chat for a while. Thank you.
Thank you very much, Sanjay. So I guess we open the floor for questions now. If you have any questions, please feel free to unmute and start asking so that we can facilitate the discussion through this.
So I can start. So Professor Shakkottai, you mentioned a SINR or CQI to MCS mapping. Did you try creating a map to other scheduling parameters, like other MIMO parameters, for example, not just the MCS, because that will determine the actual rate given to the user?
Not yet. We are doing something more now in terms of actually, so the answer is no. We are very interested in doing other parameters as well. We are playing with it. There's another direction as well we have been playing with, which is user-side clustering. So here we are trying to find maps for groups of users. However, when a new user comes in, so one thing you could have said is, but you didn't do any dynamics where users come and go in the system. What happens in that kind of a setting? Do you relearn everything every time a new user comes in? The answer is, with the kinds of things in today's talk, at least, the answer has to be yes. But maybe you don't need to do that. You want to actually cluster the user side as well and say, when the new user comes in, slot it into sort of saying that it's this kind of user and this is the table we should use. Can we do that as well? And something like that is working. That's what we got over the last week. We have some results on that. But this is just one. But going beyond that, Bilal, your question about other parameters, there are hundreds of parameters literally in this. Some of which are just set arbitrarily from as far as I understand. So how is there a way of sort of setting these parameters? And two, doing it such that the operators are not scared that putting these parameters will sort of kill their network, I think is a very interesting challenge moving forward. So even the learning one, I didn't address the second part of the question. How do I guarantee that these things are safe? Will I get to bad parameters? You need some other backup mechanisms. How do you design that? All those are interesting questions. I don't yet have a clean answer to these things.
So Sanjay, yeah, go ahead. Sorry, Bilal, go ahead, please.
Okay, one last question. So can UIs bring something to the table in terms of helping the node which is trying to create this mapping with all the users' data? Can individual UI provide something?
So UI is providing the basic thing here, which is ACNAC feedback, just saying whether it succeeds or not. Is there any higher quality feedback that can be provided to learn faster? I don't know. I haven't thought of it. It's a very good question. I can chat with you offline on that.
So Sanjay, what I was actually going to ask you already answered regarding the call arrivals and the dynamics in the system. So this is something that you're working on.
Yeah.
So, yeah, I think that would be very interesting to see how you resolve that problem. But it might be helpful, Sanjay, for you to sort of give some general comments, regarding how you and your students, in a sense, learned the details of this very important and useful problem, so that you could apply the right tools to solve it. So because to me, I think even formulating this problem requires understanding of the wireless system in a fairly deep and sophisticated way. And I think if you could, comment on that, that would be helpful.
Sure. Honestly, this problem of all of us have been playing with wireless scheduling for many years, and I've not even thought about this problem of where is the channel rates coming from. You just say that you do a MUI QI when you do wireless scheduling, and you're done. Where is the MUI coming from is something I didn't even think about that that's a problem till I was actually talking to our colleagues in AT&T saying, oh, let's do this. But then when we're trying to simulate some other algorithm, then where the MUI comes from was very murky. So then we started talking more about the model, and then we realized, there's this table which is really the bottleneck, which converged after many rounds of discussions internally. That this is where the bottleneck is, and not on the scheduling. We started this research trying to build a better scheduler. We ended up doing something very different.
Thanks. So essentially what you're saying is that the feedback and interactions with industry on this problem was quite useful.
Not just this, for me at least personally, I see Juni and others on this call. The problem choice has been driven by talking with people, with folks at Qualcomm or AT&T and other places to see why are we just spinning the wheels, or are we working on problems which somebody actually cares about, including the first URLC scheduling problem that came about actually in a discussion with Qualcomm before the standards came with this URLC problem. We realized that this is going to become a problem next year when we're working this problem, which is why we actually worked on this problem very early on. And we were lucky to get the Bennett Prize for the paper associated with that, actually. So I think anything which is, for me at least, any of these problems, you can make up lots of mathematical problems which are interesting, but what do you think is going to be useful? I think for me, the best way is to talk to my friends and colleagues in Qualcomm and AT&T and other places.
Yeah, thanks, Sanjay. Mingyan, did you have a question?
No, so I have been asked to step in and run the show for Ilam because he has to step away at 2. So I just wanted to make sure, that I'm happy to. Oh, you're back?
Before I leave, I just wanted to thank Sanjay and everyone for being here. I will stop the recording right now before I leave, but feel free to continue chatting if you have further questions. And again, thank you very much for everyone. And Sanjay, really a great talk. Hoping that I will ask my own questions later on at some point. Thanks again.
Thank you.